524 days into what should have been a 35-day mission, and it's turned into a nightmare. On the surface of Mars, 297 million kilometers away from Earth, sits Ingenuity, a tiny 680-gram helicopter that shouldn't exist. She's made from off-the-shelf parts you could find at home. Bits from an Android smartphone, batteries from a cordless drill, and a navigation system that works like your computer mouse. Against all odds, she's been performing brilliantly. But something is terribly wrong. The Martian winter is coming. At night, temperatures plummet to a frigid 85 degrees Celsius. As Mars drifts farther from the sun, the cold intensifies. Violent dust storms rage across the rust-colored landscape, blotting out the sky. Solar panels get covered. Power drains. Systems freeze. On her 427th day on Mars, the team at NASA's Jet Propulsion Laboratory in Southern California tries to reach her, just like they do every day. They send the signal across 297 million kilometers of space. Nothing. They try again. Still nothing. The engineers gather around their monitors, checking and rechecking the data. All the signs point to one devastating conclusion. Ingenuity is dead. After an incredible run that defied every expectation, the little helicopter that could has finally succumbed to the brutal Martian environment. But there's one thing, one final trick that might re-establish the connection. This is the story of the first aircraft to fly on another planet. A mission NASA didn't believe in. A helicopter built from spare parts on a shoestring budget. And the team that refused to let her die. 6 years. Earlier, I visited JPL 6 years ago and saw Ingenuity before she left for Mars. She was remarkably small. You could hold her in your arms. Her rotor blades looked impossibly delicate, like dragonfly wings made of carbon fiber. At the time, NASA didn't really believe in her mission. Kenneth Farley, the project scientist of the Mars 2020 Perseverance mission, didn't mince words. I've personally been opposed to it. Spending 30 days working on a technology demonstration does not further the goals directly from the science point of view. Translation. They thought it was a waste of time and money, a distraction from the real science. The skepticism was understandable. Mars has an atmosphere just 1% as dense as Earth's. Flying there would be like trying to fly at 100,000 feet altitude on Earth, 3 times higher than commercial jets cruise. The air is so thin it can barely support anything. Most Mars missions receive billions of dollars in funding. The Curiosity rover cost $2.5 billion. Perseverance cost $2.7 billion. Ingenuity? She got $80 million total, less than the budget of the movie The Martian. But this scrappy team of engineers and scientists were determined to prove a crazy concept: powered, controlled flight on another planet. To generate enough lift in Mars's thin atmosphere, Ingenuity had to be extraordinarily light. Just 1.8 kilograms, 4 pounds, total, with 680 grams for the helicopter body itself. Her rotor blades had to spin at over 2,400 rotations per minute, roughly 5 times faster than a helicopter on Earth. The design was unprecedented. Nobody had ever built anything like this. The engineers spent years testing in JPL's special chamber that could simulate Martian atmospheric pressure. They ran thousands of simulations. They broke prototype after prototype, learning what worked and what didn't. And still, nobody was sure it would actually fly when it reached Mars. On July 30th, 2020, Ingenuity launched from Earth attached to the belly of the Perseverance rover. The journey would take 7 months, traveling 470 million kilometers through the vacuum of space. On February 18, 2021, the real moment of truth arrived. Perseverance had to survive the 7 minutes of terror, entry, descent, and landing through Mars's atmosphere at speeds exceeding 12,000 miles per hour. The parachute deployed. The heat shield fell away. The Sky Crane fired its rockets and gently lowered the rover to the surface on cables. Then the cables were cut, and the crane flew away to crash at a safe distance. Perseverance had landed successfully in Jezero Crater, and attached underneath, protected by a debris shield, was Ingenuity. This marked Sol 0, her first Martian day. But Ingenuity couldn't fly immediately. She was still connected to Perseverance's power supply by an umbilical cable. For the next several weeks, the team charged her batteries, tested her systems, and prepared her for deployment. On Sol 3, they dropped the debris shield. Ingenuity saw Mars for the first time. On Sol 4, Perseverance began the deployment sequence, rotating Ingenuity from horizontal to vertical, lowering her toward the ground. This process had to be done slowly and carefully. One mistake could damage the delicate rotor blades or landing gear. On Sol 5, Ingenuity's legs touched Martian soil for the first time. The umbilical cable was severed. She was on her own. For the first time in her existence, Ingenuity had to survive a Martian night using only her own battery power. The team held their breath. If her heating system failed, if her batteries couldn't hold enough charge, she would freeze to death on her first night alone. The next morning, they received her telemetry. She had survived. For the next 2 months, the team rigorously checked every system. They ran up the rotors without taking off, testing their spin-up sequence. They tested the navigation camera. They tested the control computer. They simulated the flight thousands of times. Finally, on Sol 58, April 19, 2021, they were ready. The command was sent from Earth. Because of the communication delay, the team couldn't watch in real time. They had to wait anxiously for the data to arrive, not knowing if they'd see triumph or failure. When the telemetry finally came through, the room erupted. Ingenuity had taken off. She had climbed to 3 meters altitude, hovered for 30 seconds, rotated in place, and landed safely. Only 120 years after the Wright brothers' first flight at Kitty Hawk, humanity had achieved powered, controlled flight on another planet. Within days, they flew again. Flight 2 reached 5 meters altitude and moved laterally for the first time. Flight 3 flew 50 meters downrange and back. Flight 4 flew 133 meters. Flight 5, the final planned test, flew 129 meters and captured color photographs of the Martian surface from a new perspective. In just 1 month, they had completed 5 flights. The technology demonstration was complete. Mission accomplished. As one engineer put it, "We were a tech demo, right? A specified, narrow 30-sol mission. Get in, get out, we're done. We go to a bar and party, and that should be the end of it." But success has consequences. NASA looked at Ingenuity's success and made a decision. Keep going. Ingenuity's new mission was to assist Perseverance in the search for evidence of ancient life on Mars. She would scout ahead, gathering data in areas too risky or time-consuming for the rover to explore. She would identify interesting geological features, help plan the rover's route, and capture images from perspectives impossible from the ground. For the team, this was simultaneously thrilling and terrifying. There was no guarantee after Flight 5, one engineer recalled. "We may be dead by Flight 7. We may be dead by Flight 10. We were kind of thrown into the deep end of the pool. We had no processes or plans developed for such a thing." Until now, every flight had been meticulously planned. Every landing site had been carefully selected and analyzed by both satellites orbiting Mars and the Perseverance rover itself. The flights had been tested hundreds of times in JPL's wind tunnel and tens of thousands of times in computer simulations. But now they had to keep pace with a moving rover. They'd be flying into unknown territory, areas they'd never seen up close, terrain that might hide dangers. Flying Ingenuity isn't like remotely piloting a drone on Earth. At its closest approach, Mars is 56 million kilometers from Earth. At its farthest, it's over 400 million kilometers away. This creates a communication time delay of at least 6 minutes for a signal to travel from Earth to Mars and back, sometimes over 40 minutes when the planets are on opposite sides of the Sun. Ingenuity's maximum flight time is just 2 minutes. This means she must fly completely autonomously. There's no joystick control, no real-time video feed, no human pilot making split-second decisions. Instead, the process works like this. Engineers at JPL program a flight plan: waypoints, altitude, speed, heading. They upload this plan to Ingenuity. She executes the entire flight on her own, makes all the decisions, and only afterward sends back the data showing what happened. If something goes wrong during the flight, Earth can't help. Ingenuity has to save herself. You might think Ingenuity would use GPS for navigation, but GPS doesn't exist on Mars. On Earth, GPS requires a constellation of at least 24 satellites providing full global coverage. Mars has only 7 satellites total, and they're designed for communication and observation, not navigation. So Ingenuity uses something far simpler and more elegant: visual odometry. She has 2 cameras: a forward-facing 13-megapixel color camera for capturing images, and a downward-facing black and white navigation camera. This navigation camera is the key to her survival. During flight, the downward camera captures 30 images per second, 30 frames every second of the Martian surface passing below. Ingenuity's computer analyzes each image in real time, identifying distinct features on the surface: rocks, shadows, dunes, craters. Between frames, the computer tracks how these features move through the camera's field of view. It's exactly like an optical computer mouse on a mousepad. Your optical mouse doesn't know where on the mousepad it is, one engineer explained, but when you move to the right, it knows you move to the right. It's looking at features on the surface of the mousepad and watching them move under its field of view. Ingenuity does the same thing. She looks at the Martian surface, picks out features like rocks, and between camera images says, "This rock moved this way, that crater moved that way." From this movement, she calculates, "I was here, and now I'm here relative to where I started." By integrating these movements over time, she builds a map of her position and can navigate to her programmed waypoints. It's a brilliant system, elegant, efficient. But it's not foolproof. Flight 6 was supposed to be routine, the first time Ingenuity would leave her carefully mapped testing area and fly into new territory. The plan called for a 2-15-meter flight to the southwest, climbing to 10 meters altitude. 54 seconds into the flight, something went catastrophically wrong. Ingenuity began wobbling wildly, tilting 20 degrees at a time. Her emergency alarms blared. Her control system fought to maintain stability. She was lurching through the Martian sky like a drunk bumblebee, barely maintaining altitude. When the telemetry reached Earth, the team's hearts sank. They watched the data replay and saw the helicopter nearly lose control. Somehow, just barely, she had managed to land safely. But it had been terrifyingly close to a crash. What happened? The investigation revealed a software timing issue. The color camera had been added late in Ingenuity's development, leaving little time for integration testing. During Flight 6, one of the color camera's images arrived at the computer at the exact same moment as a black and white navigation image. The system didn't know what to do with 2 simultaneous images, so it dropped the black and white image. This doesn't sound catastrophic, but it had a cascading effect. Every subsequent navigation image was now 1 frame behind where it should be in the sequence. The computer was receiving outdated position data. Here's why that's deadly. When Ingenuity's computer thinks she's lagging behind where she should be, it commands her to speed up and move forward. But she's actually already in the correct position. The computer just doesn't know it yet because the images are delayed. So she overshoots. The computer sees this, 1 frame late, and commands a correction in the opposite direction. But this correction is also based on outdated data, so she overshoots again. Each correction makes the problem worse, a positive feedback loop that causes increasingly violent oscillations. It's called a death spiral in flight dynamics. And Ingenuity was on the edge of one. Only her emergency systems saved her. When the oscillations exceeded safety thresholds, she initiated an emergency landing sequence, fired her rotors at maximum power to arrest the descent, and dropped to the surface harder than normal but intact. The team quickly identified the timing bug and patched the software. Crisis averted. But it was a stark reminder. Ingenuity was flying on the edge of disaster. One wrong calculation, one software bug, one unexpected environmental condition could end the mission in an instant. Over the next dozen flights, she kept pace with Perseverance and supported the science mission, scouting ahead and capturing images of potential targets. That is, until Flight 19. "We were about to fly that 19th flight," recalled one engineer, "and I got a phone call the afternoon before basically saying there's a dust storm brewing near Jezero Crater." They immediately canceled the flight. There was nothing to do but hunker down and hope Ingenuity could survive what was coming. Mars is infamous for its dust storms. Unlike Earth, where water vapor and complex weather systems dominate, Mars has a thin, dry atmosphere dominated by dust. The planet-wide dust storms that occasionally engulf Mars can last for months and block out the sun completely. The storm that hit Jezero wasn't planet-wide, but it was still massive by any reasonable standard. It lasted 6 days, with wind gusts reaching 20 meters per second, about 45 miles per hour. For a delicate helicopter weighing less than 2 kilograms, these were hurricane-force winds. That first dust storm in the middle of fall, the first Martian year we were on the surface, one team member said, it clobbered us. When the storm finally cleared, the team nervously sent a signal to Ingenuity. Would she respond? Or had the winds toppled her over, or covered her completely in sand? The response came back. She had survived. She hadn't died or toppled over. But now they had two serious problems, and neither had easy solutions. Ingenuity's power comes entirely from solar panels mounted above her rotor blades. These panels charge her batteries during the Martian day, storing enough energy to fly and, critically, to survive the freezing nights. The dust storm had deposited a layer of fine Martian dust across these panels, reducing their power output by 18%. This might not sound like much, but in an energy-starved environment like Mars, it was potentially catastrophic. JPL had anticipated this problem during the design phase, but they simply hadn't had the time or budget to solve it. Earth's rovers like Spirit and Opportunity had carried motorized brushes to clean their solar panels, but those systems added weight and complexity. Ingenuity had neither to spare. So the team had to accept the reality. Reduced solar power meant shorter flights and longer charging times. They adjusted their flight plans accordingly, flying less frequently and for shorter durations. The second problem was even more concerning. Dust had infiltrated Ingenuity's mechanical components, particularly her swash plate servos, the actuators that control the pitch of her rotor blades. When they attempted to prepare for Flight 19, they commanded the servos to move, and nothing happened. The servos were stuck, jammed with dust particles. Without functioning servos, Ingenuity couldn't control her rotor blade pitch. Without blade pitch control, she couldn't steer. She'd be completely unable to fly. Again, JPL had known this was a risk, but hadn't had the resources to fully seal the mechanical systems. The best they could do was find a workaround. They repeatedly commanded the servos to move back and forth, wiggling them, until the mechanical motion cleared enough dust for them to operate. It worked, but it was a temporary solution. The dust would return. It always does on Mars. So she's able to keep flying, albeit wounded, one engineer said, and survival isn't getting any easier. Every Martian night presents a thermal challenge. My friend Alex from the YouTube channel Astrum explains it well. With less atmosphere, Mars became far worse at retaining heat. When the surface starts to cool, there is no air to catch the escaping warmth. It is at the point where, if you were to stand on the planet's equator during its warmest time of the day, your feet might feel 23 °C, while at your head, it would be 0°C. This dramatic temperature gradient means Mars experiences extreme day-night temperature swings. Daytime temperatures can reach 27°C at the equator, but nighttime temperatures plunge to 133°C at the poles. These massive shifts create two deadly problems for Ingenuity. First, thermal stress on electronics. Many of Ingenuity's key electrical components are hand-soldered, delicate connections made by human technicians before launch. Metal expands when heated and contracts when cooled. Over hundreds of day-night cycles, these expansion and contraction cycles can fatigue the metal and break the solder joints. One broken connection could kill an entire system. Second, battery freezing. Inside Ingenuity's batteries, a liquid electrolyte solution allows lithium ions to move between the cathode and anode during charging and discharging. This electrochemical process is what stores and releases electrical energy. But if the electrolyte solution freezes solid, the battery stops working entirely. And unlike water, which can freeze and thaw multiple times, battery electrolytes can suffer permanent damage from freezing. JPL's solution was a thermally insulated warm box that contains all the temperature-sensitive components. Inside this box, resistance heaters run during the cold Martian nights, keeping everything above the critical freezing temperatures. But here's the brutal reality. You might spend 25 or 30% of your battery energy flying, one engineer explained, and the other 60 to 75% is all just staying warm at night. Think about that. Ingenuity spends 3 times more energy simply surviving than she does flying. And as Mars moved farther from the sun and winter approached, the nights got colder. The heaters had to work harder. Battery efficiency decreased in the cold. A vicious cycle began. If the heaters couldn't keep up and the batteries cooled too much, they'd become less efficient. This would supply even less power to the heaters. Performance would continue to degrade in a death spiral. The team knew this was inevitable. It was just a question of when. The answer came on Sol 427. On the morning of May 3, 2022, the team at JPL went about what should have been a normal day. They checked the data from Perseverance's previous downlink, looking for Ingenuity's health telemetry. Nothing. That was unusual, but not unprecedented. Sometimes the communication link between Ingenuity and Perseverance gets interrupted. Sometimes the rover is positioned wrong and can't receive Ingenuity's signals. Sometimes atmospheric conditions interfere. They sent a ping directly to Ingenuity, commanding her to respond. Still, nothing. Now the concern turned to alarm. They pinged again and again. Each time the result was the same. Silence. Have they finally lost her? One engineer wondered aloud. Did we just lose our $70 million helicopter on Mars? Is this the end of the mission? The team gathered for an emergency meeting. They looked at all the available data. Ingenuity's last known battery level, the local weather conditions, the temperature readings from Perseverance, the timeline of solar illumination. The conclusion looked grim. We thought this was it, one team member recalled. But before giving up, they decided to work through every possible scenario. So let's just make sure before we close the door on Ingenuity, we've thought of everything. Just keep working through it. They ran through potential failures systematically. Communication system? Unlikely, it had been working fine. Navigation system? Irrelevant when she's on the ground. Solar panels? Covered in dust but still functional. Batteries? That was the most likely culprit. Then someone had an insight. The way she was designed, Ginny has an alarm clock that wakes her up, an engineer explained. It stays awake for 15 minutes. If it doesn't hear anything after 15 minutes, it goes back to sleep, and it doesn't wake up until the next alarm. Under normal operations, this works perfectly. Ingenuity wakes up at a predetermined time, checks for communications from Perseverance, performs housekeeping tasks, and either goes back to sleep or executes flight commands. But here's the crucial detail. If Ingenuity's batteries completely drained, if she lost all power, her internal clock would reset to 0. The hypothesis was this. The combination of reduced solar power, from dust-covered panels, extreme cold, from the deepening winter, and insufficient battery capacity had created a perfect storm. On one particularly cold night, Ingenuity's batteries had depleted completely. Her heaters had stopped. The warm box had frozen. When the sun rose the next morning, if her essential components were still intact, her solar panels would begin recharging the batteries. Eventually, she'd have enough power to boot up her computer. But now her clock would be reset. She wouldn't wake up at the programmed time JPL had been checking. She'd wake up based on when the sun provided enough power to her solar panels, essentially local sunrise. The team ran the calculations. If this hypothesis was correct, based on the sun's position and angle, Ingenuity should wake up at approximately 11:45 a.m. Martian local time. That was not the time they had been trying to contact her. It was a long shot. If the cold had damaged any critical components, if the batteries had suffered permanent damage from deep discharge, if any of 1,000 things had gone wrong, this wouldn't work. But it was their only remaining hope. They programmed the Deep Space Network to send signals to Mars during the new predicted wake window. Then they waited. Hours passed. The signal crossed 297 million kilometers of space. JPL sent ping after ping, calling out to Ingenuity at her new wake-up time. And then, finally, a response came back. She was alive. The relief was overwhelming, but it was quickly followed by worry. Had the deep freeze damaged her systems? The components in her warm box were only rated to operate down to 45 degrees Celsius. During the night when her heaters failed, temperatures had plunged far below that, possibly below 80 degrees C. They commanded Ingenuity to run a full systems diagnostic. Most systems checked out. Solar panels working, batteries charging, communication system functional, navigation camera operational, flight computer responsive. But there was one critical failure: the inclinometer was dead. The inclinometer is a sensor that measures Ingenuity's physical orientation in three-dimensional space. It tells her which way is up, how much she's tilted in pitch, forward, backward, and how much she's tilted in roll, side to side. This information is absolutely critical before flight. When Ingenuity's rotors spin up, she needs to know her exact starting orientation to calculate the correct blade pitch angles for takeoff. If she thinks she's level but she's actually tilted 10 degrees, she'll apply the wrong control inputs and immediately crash. You can imagine if you're off and heading by 10 degrees, one engineer said. You could fly into a mountain. Without a functioning inclinometer, there was simply no way for Ingenuity to fly safely. The team was stumped. They'd survived the deep freeze, re-established contact, and now they were grounded by a single failed sensor. After everything Ingenuity had been through, was this how the mission would end? Not with a crash or a dust storm, but with a single frozen component? Then someone had an idea. Remember, one engineer said during the troubleshooting session, Ingenuity is made of phone parts. Literally parts from phones people carry around every day. This wasn't an exaggeration. When JPL designed Ingenuity on a tight budget, they made a radical decision. Instead of using expensive space-rated components, they'd use commercial off-the-shelf parts and test them thoroughly. Ingenuity's main processor is from a Samsung Galaxy S5 smartphone. Her sensors include components from a Google Pixel 3. Even her battery cells are modified versions of lithium-ion cells you'd find in power tools. This approach was controversial. Traditional aerospace engineering insists on space-rated components that can withstand radiation, extreme temperatures, and the harsh environment of space. These components are expensive, sometimes costing thousands of dollars each, and take years to develop and certify. But Ingenuity proved an alternative approach. Buy commercial components, test them extensively, and fly the ones that survive. It's faster, cheaper, and in many cases just as reliable. If you'd asked somebody 10 years ago, can you fly just the latest cell phone processor? One engineer recalled, they'd be like, no, it'll last like 2 days and you'll be dead, right? It turns out that cosmic ray bit flips are not as big a deal as NASA thought. Cosmic rays, high-energy particles from space, can strike computer memory and flip bits, turning a 0 into a 1 or vice versa. On Earth, our atmosphere shields us from most cosmic rays. On Mars, with its thin atmosphere, they're far more common. In theory, these bit flips could cause computers to crash or make errors. But in practice, Ingenuity's off-the-shelf components held up remarkably well. The occasional bit flip happened, but error correction codes and redundant systems caught most problems before they became critical. And now, these phone parts would save the mission again. These phones can do a lot of the things that an inclinometer can do, someone pointed out. They have accelerometers and gyroscopes. Inside every modern smartphone is an IMU, an inertial measurement unit. This tiny device contains multiple sensors. Accelerometers measure acceleration in 3 axes, X, Y, Z. At their core is a microscopic mass suspended by flexible arms that act like springs. When the device accelerates, the mass moves relative to the frame. By measuring this displacement using capacitive sensing, you can calculate acceleration. The physics is elegant. The springs follow Hooke's law, F, Cox, force is proportional to displacement, and the mass follows Newton's second law, F, ma, force equals mass times acceleration. Combine them, me, eos, kx. So a neos kx EX m. Acceleration is proportional to displacement. The accelerometer measures displacement by using the mass and surrounding structures as a capacitor. As the gap between them changes, the capacitance changes. See Bach-Ors, AAD, where E is permittivity, A is area, and D is distance. By measuring capacitance changes, you determine displacement and thus acceleration. Gyroscopes measure rotational velocity, how fast the device is spinning around each axis. Modern MEMS, micro-electromechanical systems. Gyroscopes use the Coriolis effect. When a vibrating mass is rotated, it experiences a force perpendicular to both the vibration and rotation. By measuring this force, you calculate rotation rate. Together, accelerometers and gyroscopes form an IMU. Your smartphone uses this to rotate the screen, track your steps, play motion-controlled games, and provide navigation when GPS is unavailable. And crucially for Ingenuity, an IMU can measure orientation. When stationary, an accelerometer detects the direction of gravity, which way is down. From this, you can calculate pitch and roll angles. The gyroscopes provide additional information about rotational changes. The inclinometer is really just accelerometers that allow us to tell the initial attitude of the vehicle in roll and pitch, one engineer explained. And the IMU also has accelerometers, so in principle, it gives you the same information. The solution was clear. Reprogram Ingenuity's flight computer to use the IMU data instead of the dead inclinometer. But there was a catch. The inclinometer was a space-rated component designed specifically for aerospace applications. It was calibrated, certified, and reliable. The IMU from a Google Pixel 3? Not so much. The IMU isn't space-grade, one engineer admitted. In fact, none of these off-the-shelf parts are. Smartphone IMUs are designed for consumer applications where precision isn't critical and failures aren't catastrophic. If your phone's step counter is off by 10%, nobody dies. If Ingenuity's orientation measurement is off by 10%, she crashes. Moreover, the IMU was never intended to be used for this purpose. JPL's software was designed around the inclinometer's data format and accuracy characteristics. They'd have to rewrite significant portions of the flight control code, validate it through testing, and hope it worked on the first try, because they couldn't exactly bring Ingenuity back to Earth for debugging. The team worked around the clock. Programmers rewrote code. Engineers ran simulations. They tested every edge case they could think of. Finally, they uploaded the new software to Mars. The moment of truth came when they commanded Ingenuity to run her pre-flight checks with the new IMU-based orientation system. It worked. From the clutches of failure, they got her running again, someone said with relief. We got lucky in that the one instrument we could afford to lose was the one that died. Ingenuity was flight-ready again. What's remarkable is how well these commercial components survived on Mars. The cosmic ray environment is harsh, much worse than in low Earth orbit, where spacecraft like the International Space Station operate behind Earth's protective magnetosphere. Yet Ingenuity's smartphone processor, consumer-grade sensors, and commercial battery cells survived for over 500 sols, more than a full Martian year, with only minimal issues. Rather than going through all of the development cost of building up a processor from scratch to be radiation tolerant, one engineer reflected, our finding is you get a lot better bang for your buck by just buying batches of different processors and qualifying them. The qualification process is straightforward. Buy multiple units of a commercial component. Subject them to radiation testing. Bombard them with high-energy particles in a laboratory. Measure their failure rates and failure modes. Select the ones that perform best. Throw them through a radiation test campaign, look at the failure rates, figure out, hey, this guy, we don't know why, but for whatever reason this processor over here is great. It holds up, so we'll fly that. It's a paradigm shift in aerospace engineering. Instead of spending years and millions of dollars developing custom space-rated hardware, you can spend weeks and thousands of dollars testing commercial hardware until you find something that works. This approach won't work for every mission. A deep space probe to Jupiter's radiation-intense environment would still need specialized components. But for Mars, the Moon, and near-Earth operations, commercial off-the-shelf components are game-changing. Ingenuity proved it. And future Mars helicopters will benefit from this knowledge. Using these surprisingly robust off-the-shelf parts, Ingenuity survived the rest of winter. Just barely, but she survived. Springtime came, one engineer said with obvious relief. Talk about spring optimism, right? Coming out of winter. As Mars's orbit brought it closer to the sun, the days grew longer and warmer. Solar illumination increased. Dust devils, small whirlwinds that naturally form in Mars's thin atmosphere, began sweeping across the landscape, clearing some of the dust from Ingenuity's solar panels. Power generation improved. Battery charging became more efficient. The brutal cold that had nearly killed Ingenuity eased into something merely challenging. With increased sunlight, she could now fully recharge her batteries and return to her scientific mission. Perseverance had been patiently waiting, unable to venture into certain areas without aerial reconnaissance. Now, Ingenuity could scout ahead again. Over the next 41 flights, flights 31 through 71, Ingenuity and Perseverance worked as a team exploring Jezero Crater in ways that would have been impossible with the rover alone. Ingenuity imaged craters that Perseverance couldn't safely reach. Some were too steep, with loose sand that might trap the rover's wheels. Others were surrounded by boulder fields that posed collision risks. But from the air, Ingenuity could fly over these obstacles and capture detailed photographs. She captured stunning images of the Martian horizon from above, showing vistas that humans had never seen from this perspective. These weren't just pretty pictures. They were scientifically valuable, showing geological features, rock distributions, and terrain characteristics that informed the mission's geological interpretations. She conducted daring aerodynamic tests, pushing the boundaries of what was considered safe. The team wanted to understand exactly what Ingenuity was capable of, what her limits were. This knowledge would inform the design of future Mars aircraft. One of the biggest questions was, how fast could Ingenuity fly? Initially, they had kept speeds conservative, around 2 meters per second, about 4.5 kilometers. This was deliberate caution while they learned how the navigation system performed in real Martian conditions. But now, they wanted to go faster. There was just one problem. The faster Ingenuity flew, the quicker surface features moved across her navigation camera's field of view. And her vision navigation system couldn't keep up with rapid movement. Think back to the optical mouse analogy. If you move a mouse slowly across a mousepad, it tracks perfectly. But if you swipe it really fast, it sometimes loses tracking because features blur past the sensor faster than it can process them. Ingenuity faced the same limitation. At higher speeds, rocks and craters zipped past her downward camera so quickly that her computer struggled to identify and track them between frames. The navigation solution would become unreliable, potentially leading to position errors and crashes. But the team came up with an elegant solution. Fly higher. By increasing altitude, they expanded the camera's field of view. The same rock that appeared to move quickly at 3 meters altitude would appear to move more slowly at 12 meters altitude. Just like how clouds seem to move slowly when you're on the ground. But if you're in an airplane, they seem to crawl even though you're moving much faster. So, from an initial goal of a 10-meter altitude, one engineer explained, they went up to 24 meters. This altitude increase had the desired effect. Features moved more slowly through the camera frame relative to Ingenuity's actual speed. The navigation system could track reliably again. And as a result, they were able to go from flying at 2 meters per second all the way up to 10 meters per second. That's 22 miles per hour, over 5 times the initial flight speed. For a helicopter operating on Mars with just 1% of Earth's atmospheric density, this was extraordinary. Speed records, distance records, altitude records, just everything we could think of to push that flight envelope on Ingenuity, one team member said with pride. Really make the most of this once-in-a-lifetime opportunity of having a helicopter on Mars. By Flight 70, Ingenuity had flown a total of 17 kilometers across the Martian surface, achieved a maximum flight distance of 704 meters in a single flight, reached altitudes up to 24 meters, sustained speeds of 10 meters per second, logged over 128 minutes of total flight time. These weren't just numbers. Each record represented a boundary pushed, a limit tested, valuable data collected for future missions. Everything was going swimmingly. Ingenuity and perseverance had made it all the way to Neritva Vallis, an ancient river delta in Jezero Crater. This was exactly where NASA wanted to go, a place where liquid water once flowed billions of years ago, potentially creating conditions suitable for ancient microbial life. But on Flight 71, there was a new problem, and it was worse than any that had come before. Now, Ingenuity's only scientific payload was her camera. She took hundreds of photos every day, sending them back to JPL. She and Perseverance were the most chronically online duo on Mars, constantly sharing data about their location, status, and observations. By Flight 71, they had a specific objective: cross a field of sand dunes to reach an area called Bright Angel, where Perseverance needed aerial reconnaissance before committing to the route. "So we just had this one final thing to do," an engineer recalled. "We needed to cross this sand dune and make it to Bright Angel to rendezvous with the rover." The flight plan seemed straightforward: fly over the dune field, capture images, and land on the other side. So, on 71, we basically went up. We were flying. And then after about 10 seconds of flying with degraded navigation, we went into an emergency landing mode and sort of came down hard. The problem was the sand itself. Unlike the rocky terrain Ingenuity had been flying over for most of her mission, sand dunes are remarkably featureless. There are no distinct rocks to track, no clear shadows, no sharp-edged craters, just smooth rippling sand that looks essentially the same in every direction. Remember, Ingenuity navigates by tracking distinct features between camera frames. But when there are no distinct features to track, her navigation system goes blind. It's like trying to use that optical mouse on a blank white piece of paper. The mouse sensor can't identify any features, so it can't tell that it's moving. From the mouse's perspective, it's stationary even when you're moving it across the surface. Ingenuity faced the same problem over the sand dunes. Her camera captured images of sand. Then more sand. Then more sand. No rocks, no distinctive features. Her computer couldn't establish a reliable position reference. Within seconds, her navigation confidence dropped below safe thresholds. Emergency protocols activated. She executed an immediate landing sequence, dropping to the surface harder than normal, but avoiding a complete loss of control. They hailed Ingenuity. "Fortunately," she responded. They checked her error logs and discovered the navigation issue. They also checked for structural damage from the hard landing. Surprisingly, everything appeared intact. No broken components, no damaged rotors. The landing gear had absorbed the impact, and all systems reported nominal status. "So they attempt another flight," one engineer said. "This time going straight up to scan the surroundings and then coming straight back down. Simple." The idea was sound. If they flew straight up from the same spot, they'd have the same features visible during ascent and descent, making navigation easier. They'd avoid crossing the featureless sand dunes horizontally. Flight 72 was programmed for a simple vertical profile: ascend to 12 meters, hover briefly while capturing images of the surrounding terrain, then descend back to the same landing spot. We popped up, took pictures, and then on the way back down we hit the same problems we did on 71. Once again, the featureless sand caused navigation degradation. Once again, Ingenuity initiated an emergency landing, but this time it was fatal. Perseverance drove over to Ingenuity's landing site and captured images that broke the team's hearts. The photographs showed Ingenuity upright on the sand, but her rotor blades were destroyed. All 4 blades had broken off, scattered around the landing site like shrapnel from an explosion. "When we saw the blades broken, when we saw that first image after Flight 72, that was heart-wrenching," one team member said. "It was like, no, there's no way this mission can continue. That was very depressing." The mission was over. After 72 flights, 524 souls, over 17 kilometers traveled, and countless obstacles overcome, Ingenuity's flying days had ended in a sand dune field. But the team had questions. Why did Flight 71's hard landing leave Ingenuity intact, while Flight 72's apparently similar landing destroyed her? Both were emergency landings caused by navigation issues. Both came down on sand. What was different? This is the first air crash investigation on another planet, right? Someone asked. Yeah, that's right, came the reply. First aircraft on another planet and then the first air crash investigation kind of go hand in hand. The team analyzed every piece of available data: telemetry from the flight, images from Perseverance, photographs from Ingenuity's own cameras before she lost power. They studied the landing site, looking for clues about what had gone wrong. They noticed something strange. We noticed something interesting, which was there was no blade strike spot, one investigator explained. Blades spinning this fast, when they hit the ground, right? They're going to create a spray. There's going to be a pattern, probably even visible from orbit, and we didn't see anything like that. This was puzzling. If the rotor blades had struck the ground while spinning at 2,400 RPM, they should have gouged deep marks into the sand and scattered material in distinctive radial patterns. But there were no such marks. So if the blades didn't strike the ground, what broke them? To understand what happened, you need to understand how helicopter rotors behave under stress. One of the JPL engineers showed me an actual prototype blade from Ingenuity's development phase. This is essentially identical to the blades on Ingenuity, he said, handing it to me. It's a carbon fiber composite with a foam core. The blade was incredibly light, perhaps a quarter of what I expected just from looking at it. It almost didn't feel physical, like holding a stage prop instead of an actual aircraft component. It's incredibly light, I said. That's like at least a quarter of what I expected. It doesn't feel physical. But this lightweight construction, while essential for Mars flight, came with vulnerabilities. So why did they break? The engineer asked, then began explaining the physics. As the blades spin, the tips of the blades trace out a circle, which you can think of like a hula hoop. If there's a force up on the near side, you might expect the rotor to tilt immediately in this direction. He gestured to show a rotor disc and an upward force applied to one side. But that is not actually what happens. See, the blade isn't stationary. It's moving really fast. So when you apply this force, it actually only moves after that point. So the maximum displacement occurs 90 degrees later. This is the principle of precession, the same physics that explains gyroscope behavior. So even though we push up on the near side, the blades tilt up on the right and down on the left. This effect is called precession, and it's the same principle that explains this spinning bike wheel demonstration. Ingenuity has two sets of counter-rotating blades, one set spinning clockwise, the other counterclockwise. This design cancels out the gyroscopic torques on the helicopter body, allowing stable flight. But each individual blade still flexes because of that precession torque, he continued. That results in a stress concentration right about here, where that final reinforcement tapers off. He pointed to a spot about 2/3 of the way along the blade's length, where the internal carbon fiber reinforcement decreased in thickness. And so, if you had a precession-based failure, you'd expect it to fail right here. And sure enough, that's exactly where you see it in the pictures. The photographs from Perseverance confirmed it. Each blade had snapped at precisely that location, leaving a jagged break where the reinforcement tapered down. So here's the sequence of events on Flight 72. Ingenuity ascended successfully, captured her photographs, and began descending. Over the featureless sand, her navigation degraded. She initiated an emergency landing, but because she had poor position awareness, she came down at an angle, tilted relative to the surface. When her landing gear struck the sand, the impact force wasn't absorbed vertically through the struts as designed. Instead, it came in at an angle. This asymmetric force was transmitted up through the fuselage and into the rotor system. The rotors were still spinning at high speed. Ingenuity doesn't completely stop the rotors before landing. She keeps them spinning to maintain control authority until the landing gear makes contact. The angled impact created a complex force on the spinning rotor disc. Due to precession, this force manifested 90 degrees around the rotation from where it was applied. The blades bent under this precession-induced torque. But the blades weren't designed to withstand this kind of lateral bending force. The stress concentration at the reinforcement taper point exceeded the carbon fiber's ultimate strength. Snap. All four blades broke almost simultaneously. "This thing came down hard," one engineer said, examining the data. "It didn't destroy the landing gear. It didn't break the avionics. It didn't kill the servos. The swash plates are all fine. They're all intact. It's the rotors. That's the weak link." In a way, this was fortunate. If the landing gear had failed, if the electronics had been destroyed, if the flight computer had been damaged, there would be no opportunity to learn from the failure. But because only the rotors broke, a mechanical component whose failure mode was now well understood, JPL gained invaluable data for future designs. "So that is the first thing they're changing on the next generation of Mars helicopter," the engineer explained, "which is called Chopper." He handed me a different rotor blade, this one noticeably more robust than Ingenuity's. "You had a chance to hold the Ingenuity blade. This is the next-gen baby blade." I examined it carefully. "It looks fairly similar with a couple of key differences. They reinforced the blades to withstand the torques caused by hard landings," he confirmed. "The new blade maintained the same lightweight carbon fiber and foam construction, but the reinforcement didn't taper as dramatically. The stress concentration point that had been Ingenuity's weakness was now distributed more evenly along the blade's length. But that wasn't the only improvement. Now they also have 6 rotors instead of 2, which means Chopper can hold a lot, even carrying a scientific payload of its own. This was a game changer. Ingenuity was purely a technology demonstrator and scout. Her only scientific instrument was a camera. Chopper would be a true scientific platform, capable of carrying instruments directly to sites of interest. "We've developed now a very lightweight radio that can communicate directly to orbit," the engineer said with obvious excitement. "Whoa," I responded. "So you're a free bird when it comes to exploring the planet now." "That's huge. You were sort of trying to trail Perseverance, right? And now you can go anywhere." "Yep, we're our own spacecraft." This was perhaps the most significant advancement. Ingenuity had been tethered to Perseverance by the need for communication relay. She could only fly within a few kilometers of the rover, and all her data had to be relayed through Perseverance to the Mars orbiters and then to Earth. Chopper would communicate directly with Mars orbiters, the same satellites that communicate with rovers. This meant complete operational independence. "In this blue box," he gestured to a payload compartment on the Chopper model, "you can shove about 5 kilograms of science payload and bring it anywhere on the planet Mars. You can fly 3 kilometers per sol in a matter of minutes. That's really generated a lot of excitement in the science community. 5 kilograms might not sound like much, but for Mars exploration, it's revolutionary. That's enough mass budget for a sophisticated spectrometer to analyze rock composition, a ground-penetrating radar to probe subsurface structure, a seismometer to study Mars quakes, a microscopic imager for close-up photography, sample collection tools for cached return missions. And delivering these instruments 3 kilometers per day, something that takes a rover weeks or months to achieve, opens up entirely new exploration strategies." They showed me a 5th-scale model of the complete Chopper system. It was really 2 integrated systems, the helicopter itself, and underneath it, a rocket-powered delivery platform. "This is our Chopper platform, right? This is what's going to go on and explore the entire surface of Mars one day. That's the point of the concept. But underneath is a mid-air helicopter delivery platform." The concept was brilliant. Mars rovers need complex sky crane systems for landing, the same system that lowered Perseverance and Curiosity to the surface. These systems are expensive, heavy, and require precise engineering. But a helicopter doesn't need a sky crane. It just needs something to take off from. The idea is we come down through the atmosphere, we have this jetpack that we need to slow us down to get us down to a regime that is controllable so that we can take off from that platform mid-air and land under our own power. Here's how it would work. Chopper enters Mars's atmosphere inside a protective heat shield, just like any Mars mission. As it descends, a parachute deploys to slow it down. At a few hundred meters altitude, the heat shield is jettisoned. Then, Instead of a sky crane lowering a rover to the surface, the delivery platform fires rockets to arrest the descent and stabilize the system in midair. Chopper's rotors spin up. When ready, the helicopter simply flies away from the rocket platform, which then crashes at a safe distance. For this, it needs rockets, I observed. 3, 2, 1. The test video showed a scale model's rockets firing, creating a stable hover platform. Awesome, I said, genuinely impressed. You're envisioning like a future of aviation all over Mars as a primary explorative tool? In my mind, it's absolutely going to happen in just a matter of time, the engineer replied with conviction. There will be fleets flying throughout Mars. There will be airports on Mars one day, and we'll have aircraft the size of Chopper, more aircraft the size of Ingenuity, and even bigger than Chopper. This wasn't science fiction speculation. It was engineering roadmap. NASA is serious about Mars aviation, and it's all thanks to Ingenuity proving the concept. Think about what this means. Instead of spending months driving a rover across dangerous terrain, a fleet of helicopters could survey hundreds of square kilometers in days. They could access locations rovers can never reach. Steep crater walls, isolated mesas, deep valleys, polar ice cliffs. They could work as a coordinated network. One helicopter carries a drilling system, another carries analytical instruments, a third collects samples and caches them for return missions. They could establish remote weather stations across the planet, creating a comprehensive climate monitoring network. And eventually, as human missions to Mars become reality, helicopters could scout landing sites, deliver supplies between habitats, conduct search and rescue operations, and provide aerial transportation across the Martian landscape. NASA is thinking big thanks to Ingenuity, a project they once doubted and nearly canceled. In 1890, if you had said, "I'm gonna fly," it's like, okay, that kooky guy in his garage, he thinks he can fly. He's gonna kill himself, right? One engineer reflected. After the Wright brothers, it's like, oh, okay, yeah, this is the thing that we're gonna do. And so that's the change in mentality that's occurred because of Ingenuity. Before Ingenuity, Mars aviation was theoretical. Interesting papers, ambitious proposals, but no proof it would actually work. After Ingenuity's 72 flights and 17 kilometers of travel, its proven technology, the psychological shift within NASA has been dramatic. Missions that were once considered too risky or speculative are now actively being planned. Funding that would have been denied is now approved. Engineers who proposed flying missions are now leading development teams. Ingenuity changed what's considered possible. There's a detail about Ingenuity I haven't mentioned yet. Something small but profoundly symbolic. Attached to the underside of Ingenuity, carefully protected and wrapped, is a tiny scrap of fabric. Just 1 square centimeter of muslin cloth. This fabric was taken from the lower left wing of the Wright Flyer, the first airplane that Orville and Wilbur Wright flew at Kitty Hawk, North Carolina on December 17, 1903. On that cold morning, 118 years before Ingenuity's first flight, Orville Wright climbed aboard the fragile wooden aircraft. His brother Wilbur ran alongside the wing, steadying it. The engine coughed to life, spinning the twin propellers. The Wright Flyer lifted off the sand, flying 120 feet in 12 seconds before settling back to the ground. It was humanity's first powered, controlled, heavier-than-air flight. That piece of wing fabric had witnessed the moment that changed human civilization forever, the moment we left the ground and took to the skies. And now, 120 years later and 297 million kilometers away, that same fabric witnessed another first flight. The first time humanity flew on another world. From the first flight on Earth to the first flight on another planet, one team member said emotionally. From Ingenuity's grave on Mars, her spirit lives on. It's a powerful symbol. The Wright brothers flew for 12 seconds and 120 feet. Ingenuity flew for over 2 hours total and 17 kilometers. But both represented the same thing. The audacity to attempt something everyone said was impossible. The Wright brothers were told heavier-than-air flight violated the laws of physics. Ingenuity's team was told Mars aviation was impractical and unnecessary. Both proved the doubters wrong. Except, the engineer said with a slight smile, She isn't quite dead yet. After the crash, after the blades broke, after the flying mission ended, Ingenuity kept functioning. Her solar panels still charge. Her computer still operates. Her communication system still works. She's acting as a weather station now, capturing photos every day, capturing temperature measurements every day. Something no one would have ever predicted before Flight 72, that if things don't go well, we just still have a functioning spacecraft. Every Martian day, Ingenuity wakes up. She measures the temperature, atmospheric pressure, and solar illumination. She captures photographs of the surrounding terrain with her cameras. She logs data about dust accumulation on her solar panels. And she beams all of this information to Perseverance when the rover comes within communication range. She's become Mars's smallest, toughest weather station, a stationary scientific platform providing valuable, long-term environmental monitoring data. "So she's a tank," I said admiringly. "She really is," came the reply. Ingenuity taught us lessons that will shape the future of space exploration. 1. Commercial off-the-shelf components can work in space. You don't always need expensive, custom-designed, space-rated hardware. With proper testing and selection, consumer electronics can survive environments we once thought required specialized equipment. 2. Small, agile missions can achieve extraordinary results. Ingenuity cost $80 million and was considered a risky technology demonstration. She ended up producing more value per dollar than almost any other Mars mission component. 3. Simplicity and cleverness beat complexity. Ingenuity navigated without GPS using a simple downward camera. She survived temperature extremes using basic heaters. Her design was elegant because it was simple. 4. Failure teaches as much as success. Every problem Ingenuity encountered, the timing bug, the dust storm, the deep freeze, the broken inclinometer, the final crash, provided data that will make future missions better. 5. Aviation on Mars is possible and practical. This was the fundamental question Ingenuity was built to answer, and she answered it definitively over 72 flights. The team couldn't be more proud of what Ingenuity accomplished. They took a mission that was supposed to last 30 days and stretched it to 524 days. They planned for 5 flights and achieved 72. They expected to fly a few hundred meters total and covered 17 kilometers. At every step, when faced with seemingly insurmountable problems, they found solutions. Software bugs? Patch them. Dust storms? Survive them. Frozen sensors? Work around them. Limited power? Adapt to it. The ingenuity, the cleverness, resourcefulness, and creative problem-solving that went into keeping Ingenuity flying was as remarkable as the helicopter itself. One engineer summed it up perfectly. This was a mission that wasn't supposed to succeed. NASA doubted it. The science team opposed it. We had a tiny budget and an impossible challenge. But we believed in it. And look what we accomplished. As I write this, Ingenuity sits motionless on the Martian surface in Neretva Vallis, her broken rotor blades scattered around her like fallen leaves. But she's not silent. Every Martian day, as the sun rises over the rust-colored dunes, her solar panels begin generating power. Her computer boots up. Her sensors come online. She measures, records, and transmits, a tiny voice still calling out from 297 million kilometers away. Perseverance has moved on, continuing the search for signs of ancient life, drilling cores, and caching samples for eventual return to Earth. But occasionally, the rover pauses its work, turns its antenna toward the south, and listens for Ingenuity's signal. And Ingenuity is always there, always transmitting, always fighting to survive one more Martian day. That's the spirit that will take humanity to Mars. Not giving up, not accepting defeat, finding a way forward even when the mission seems impossible. From the Wright brothers' 12-second flight to Ingenuity's 72 flights on Mars, the message is the same. We can do impossible things if we dare to try. Mission status, still active mission. Duration, 524 plus, souls, and counting. Planned. Mission, 35 souls. Total flights, 72. Total distance, 17 plus kilometers. Current. Status. Weather station? Still transmitting daily, somewhere on Mars. In a valley filled with ancient river sediments, a little helicopter that refused to die keeps watch over the red planet, waiting for the day when humans finally arrive to see her accomplishments firsthand.